A vast amount of wood we harvest will likely end up being discarded before production, and even after that, a lot of it will be improperly disposed of in landfill. What if we could utilize this discarded wood, or repurpose disposed wooden products and create a new wood-like alternative material to return to the product cycle? According to reports, around 25% of wood products here in Tasmania are made using wood logged from our native forests. Native forest logging here is responsible for around 4.65 million tons of carbon emissions each year, which is the equivalent of around 1.1 million cars worth of emissions, making it Tasmania's highest emission sector. When a tree is logged, it is estimated that only 1% of its log will result in timber. 60% of what is deforested likely won't be harvested and left on the forest ground. 10% of what is collected will be turned into sawlog, and 25% of the sawlog will become timber. The wood that is discarded during the process commonly will be reduced into sawdust and disposed of into the environment. Although sawdust is biodegradable, when discarded in bulk quantities, large quantities of fatty acids and lignin may be released into the environment, harming wildlife and contaminating the grounds. Our biomaterial is a synthetic wood alternative that is created with the sawdust from the timber waste stream, or collected from shredded discarded furniture that may end up in landfill. The sawdust is combined with ground sea urchin shell in a powdered form. The shell powder provides calcium carbonate to the biomaterial, which assists in bonds being made. We use sea urchin shells for this due to the overpopulation of invasive sea urchins currently decimating kelp forests here in Tasmania. After being harvested, the sea urchins are prepared for consumption and the shells are discarded, providing a waste stream we can source from. Once the sea urchin powder and the sawdust is combined, the contents are combined with a heated mixture of water, agar, gelatin, glycerin, and xanthan gum to form a strong binder. Borax is also added to prevent mold growth. The material is then pressed into a mold and left to dry in a warm environment. Both sides of the mold are exposed to heat to reduce mold growth from the residual moisture. For our prototype design, we let our mold dry in a place of significant sunlight. After a few days, with the open sides of the mold alternating between heat exposure each day, the full casing is removed and the material's production is finished. Our material production will be sourcing ingredients from local providers and collecting from relevant waste streams. During our production, we visited a local sea urchin processing company where we were able to obtain discarded shells from their waste. The company spends significant expense, estimated around 20,000 Australian dollars, to discard the shells. Us being able to use the shells from their waste stream repurposes the waste and gives us a local supplier that would benefit from the waste collection. With our biomaterial, we intend for it to be used for small-scale applications for wooden products or furniture. Due to our material not having a fiber structure like natural wood, it's likely that it may not have the strength for any significant large-scale applications such as architecture. We believe our material would be more suitable for home appliances. For our prototype design, we made a simple clothes peg to showcase the material as a product. When our biomaterial gets to its end-of-life stage, it can safely be returned to the environment. All materials used within our biomaterial are biodegradable, and when being disposed of, including in the event of informal disposal, due to the product's small size, there is no risk of fatty acid or lignin pollution when being recycled.